Welcome to lesson 6 of chemistry. Today we're going to be looking at orbital box diagrams, which is an immediate follow-up from my last video, which was about SPDF orbitals and just orbitals in general. Okay, so starting off, what are orbital box diagrams? So as you remember, an orbital is defined as an area in space where it is likely to find an electron. Now, we talked about electron configuration last time, so I'm just going to go over a quick little example reviewing what we did. So for our first example here, we're just going to practice by writing the electron configuration of carbon. So if you look on your periodic table, you will see that carbon is element number 6. It has 6 electrons, and it is in the p block. Okay, so as you remember with the Aufbau diagram, we always want to start with 1s. So we can go 1s, and then in the first s subshell, there is 2 electrons. Following that, we have the second subshell, or the second energy level subshell, s, with 2 electrons. And after following the Aufbau diagram, after s comes p, and then seeing that we have 6 electrons, here we have 2, then 2, and then left over we would have 2. So therefore, carbon's electron configuration is 1s2, 2s2, 2s2p2. If you add all the exponents, you will get 2 plus 2 plus 2, which is 6, matching the 6 electrons around carbon. Now I'm just going to do one more quick example of phosphorus. So phosphorus has 15 electrons, and it is 2 in the p block. So starting like we did with carbon, we have 1s2 followed by 2s2, and then we can do p6 this time. And then after that, we're going to move to 3. So we go 3s2, and let's just take a break to count our electrons. So far we have 2 plus 2 is 4, 10, 12. So we have 12. We're really close. So we need to add 3 more. So after 3s comes 3p. So we go p3. So just like this is for carbon, and this is the electron configuration for phosphorus. So what are orbital box diagrams? Like, why do we use them? So we have our electron configurations, but orbital box diagrams are used as a way to visually kind of show how we're organizing our electrons and where they're going to be placed. So basically, we want to start with a graph. So let's just go with the graph here with our y-axis and our x-axis. I'll make the x-axis a little bit longer. Whoa. Perfect. And then on the y-axis, I'll just write an E for energy, for the energy levels. This bottom part isn't really needed. I just use it to make it an entire graph. So starting off, let's go with carbon, right? So we have carbon. So as we just talked about, carbon's electron configuration, or I like to think of the electron configuration as kind of like the fingerprint of an element. You know, each element has a unique fingerprint to it. You know, it's kind of like a little code that represents, well, the atom. So 1s2, 2s2, p2. This was carbon. So if we look here, we can notice that as our energy level increases, as our n value increases, that means that more energy is going to be used in those higher states, which means that if we're measuring the amount of energy on this y-axis here, that a p block, let's say we have a p block here, would be above an s block. Because all we're doing on this graph is kind of just comparing how much energy is in different subshells. So what we want to do here is with the orbital box, we want to start by making boxes. So first what we want to do is we want to go from left to right. So first we have 1s. So we can draw a little box here, right, called an orbital box, hence the name of the video. And then we want to call this 1s, We don't need the number 2. Well, I'll get to that. I'll get to y in a second. And then next we have 2s2. So keeping with this kind of s column, right? Because we want to be organized, we can use this kind of column just for s's. And then we can call this 2s. And then I'm going to switch colors here. Now we have a p. And this is the thing. Since this is the s column, we want a p orbital to be over here. We want it to be off to the side of it. It doesn't have to be this far, but I'm just doing it for demonstration. And if we remember, a p orbital, it has 6 electrons inside of it, max. There. So now we have these boxes here, right? We have this box, which shows a p orbital, and we can call it 2p. And then we have these boxes for the s orbitals. Now, how does this relate to what we talked about before? So as you remember on our graph, let's say we had the sphere, right? We had the sphere of 1s, right? In that sphere, there could be a max of 2 electrons, right? Well, if you remember the quantum number ms, it stated that electrons have a spin, and those spins are in values of plus 1/2 and minus 1/2. So how do we apply this? Well, the Pauli exclusion principle basically states that each orbital holds 2 electrons, each with opposite spins. So using the Pauli exclusion principle, we can represent this plus 1/2 as being a upwards arrow, just like that, kind of like a number 1. And we can represent this one, the minus 1/2, as being a downwards arrow, like so. So using the exclusion principle, we can put them inside of this and say that in this orbital, there is a plus 1/2 electron and a minus 1/2 spin electron. So this has plus 1/2 and minus 1/2. So we can apply this to the orbital boxes. So see, we have these boxes here, right? Well, the reason why they're boxes is so we can add electrons inside. So how many electrons do we have in the 1s block? Well, we have 2, hence the exponent. So we can go to the 1s block, we can go 1, 2. And go to the 2s, same thing, 1, 2. And then we can go to P2, right? And your first reaction might be to go 1 and 2, but this is where but this is wrong. This is where we introduce something called Hund's rule. I'll write down here. Hund's rule. So what Hund's rule basically states is that when you have a block that has more than one orbital space in it, such as like a p block, d, or an f, anything but s, what you want to do is you don't want to add your electrons like this. Like you have 1, 2, 3, 4, right? You just go plus 1/2, minus 1/2, plus 1/2, minus 1/2 in order to get each box at a time. You don't want to do that. This is a big no. What you want to do instead is, let's say in this case, just like before, we have 4 electrons that we're trying to place. So we have our 3 boxes for 4 electrons. Instead, Hund's rule says that what we should do is start with plus 1/2 and then use minus 1/2. So stick to one charge at a time. Don't switch back and forth. So using the plus 1/2 ones, these, we can go plus 1/2, plus 1/2, plus 1/2, and then we have one more electron, so we'll go minus 1/2. So this is the correct way of showing 4 electrons in a p orbital. So in this case, when we have our 2p up here, what we should do is write it like this. And just like that, we have the orbital box diagram for carbon, which basically says that increases in energy show that electrons are found in 2s orbitals and 2p orbitals. So just to refresh on what Hund's rule says, it states that every orbital in a sublevel is singly occupied before any orbital is doubly occupied. And all of the electrons in singly occupied orbitals have to have the same spin, which means that it's all equivalent in energy. And these electrons occupy the orbitals to create a structure which is the lowest possible in potential energy. And when electrons occupy the same region in space, there is more repulsion requiring more energy to contain, hence why we have the energy going upwards on this graph. So Our second example is we're going to be looking at a element that has quite more electrons than carbon. So we're going to be looking at manganese. So Mn, and manganese has 25 electrons, and putting those into electron configuration using the off-bow, we have 1s2, 2s2p6, 3s2p6, and then remember we use 4 before we go to 3. We use 4s before we go to 3d. So we go 4s2, and then 3d5. So once we add all these up, we'll have 1, 2, 3, 4, 10, 14, 20, and then 25. So let's start with the same thing we did before, and I'm gonna do it without the bottom x-axis just to show that it's really not necessary. So we can put a little tip here showing that the energy continues. So using E, or just write energy. I'll write energy this time. Energy. So starting off, like before, we have our 1s orbital, 1s, and then above that we have 2s, 2p, and then above that we have 3s. So see, I'm keeping all the columns the same, but I'm making sure that they all increase in energy proportionally. So now we have 3p, just following the trend we have listed here. And then 3p. And next we have 4s. And then we have 3d, which is going to be way off to the side here. And it's going to have 5 because it holds 10 electrons max. 1, 2, 3. Perfect. So these are our orbital boxes for manganese. Now we need to start filling electrons. So here we have 2 electrons for 1s. So we go 1, 2, same with 2s, 1, 2. And then for 2p we have 6, but then using Hund's rule we go 1, 2, 3, and then downwards 4, 5, 6. Now for 3s, just 1, 2, 3p, same as 2p, 1, 2, 3, downwards 4, 5, 6. 4s, 1, 2, and now 3d5 is going to be, sorry, I should have labeled 3d. So 3d5 is going to be 1, 2, 3, 4, 5, and that's it. So if we count it up, we'll see that we have 25 different electrons, and this basically just shows that with manganese, these are the different sublevels and energy levels in which we are most likely to find electrons.